Hello everyone. Today's topic is crystal planes and its directions. Today we will study the concept of Miller indices for planes and directions, its need, and at the end of lecture we will study the important features of Miller indices. Now before calculating the Miller indices for planes and directions, let us discuss in short what is lattice planes. As in previous lectures, we have discussed the concept of lattice, basis, crystal structures, unit cells, primitive cells, etc. And as you know, lattice is a symmetric array of points in space. We can add atoms at each lattice point in an arrangement called a basis. And these atoms can be one or group of atoms having the same spatial arrangement to get a crystal. In every case, the lattice contains a volume or a cell that represents the entire lattice and is regularly repeated throughout the crystal. So, the lattice planes are the planes passing through lattice points. For a given lattice, the lattice planes can be chosen in a different ways. Miller has introduced a system to designate a plane in a crystal. Now, let us discuss about the Miller indices and how to calculate the Miller indices for planes and directions. A set of three integers used to describe the position of a plane or the direction of a vector within the lattice. The set of these integers used to describe a crystal plane is called as the Miller indices of a plane. These integers in crystallography shown by H, K, and L. Miller indices are used to specify directions and planes. These directions and planes could be in lattices or in crystals. The number of indices will match with the dimension of lattice or the crystal. For example, in one dimensional there will be one index, two dimensional there will be two indices, while in three dimensional there will be three indices. And all parallel planes and directions have the same Miller indices. So we will discuss about this. The parallel planes and directions have the same Miller indices in next slides. What is the need of studying this, the direction and planes in crystallography? In material science, it is important to have a notation system for atomic planes, since These planes influence its optical properties, reactivity, surface tension, dislocations, etc. Now there are some notations are used in crystallography for directions and planes and the family of the directions and planes. When these integers HKL are represented in square bracket, so it represents a direction. When this integers HKL in angular bracket represents a family of directions. And when this integers HKL in round bracket represents a plane, while HKL in curly bracket represents a family of the planes. Now we shall discuss about the calculations of Miller indices for planes and the directions. Now let us start with the Miller indices for planes. A set of three integers used to describe the position of plane or the direction of a vector within the lattice. Firstly, set up an XYZ coordinate system with the origin at any lattice point and the axes are lined up with the edges of the cubic unit cell. The three integers describing a particular plane are found as follows. First, find the intercepts of the plane with the crystal axes and express these intercepts as integral multiples of basis vectors. In second step, take the reciprocals of the three integers found in step 1 and reduce these to smallest set of integers HKL which have the same relationship to each other as in three reciprocals. And finally, enclose these integers in parentheses. There should be no commas. That is the round the HKL in round bracket which represents the Miller indices for planes. And when these all planes, parallel planes, when represents in the integers of these parallel planes, when represented in curly bracket, that represents the families of these planes. Now let us take one example to calculate the parallel planes. Now in this you can take any example, arbitrary example. Let me take the pin. So if we draw here the coordinate system, XYZ coordinate system, y-axis, x-axis and z-axis. This is the origin. Draw any plane at the origin. Suppose you can represent it by A, then twice A, here is B. These are the A, B, C are the, as you know, the lattice parameters. here 1C, 2C, and so on, or simply C. If we draw any arbitrary plane, so if we draw like this, and this, so this plane. So this plane is A. Okay, take another symbols P, Q, and R. So in plane P, Q, R, according to the earlier discussion, there are 4 steps. Take the intercepts on the axes. So here along X, the intercept is twice A, then along B is 1B, and along C twice C. In second step, write its coefficients or divide by a corresponding lattice constant 1B by B, 2C by C. So therefore 2, 1, and 2 are the coefficients of these intercepts. Third step is take the reciprocals of this. One by 2, 1 by 1, and 1 by 2. So these fractions convert by multiplying by its common factor, means here in this case we have to multiply by 2. So by 2 by 2, 2 by 1, here is a 2, sorry, and again 2 by 2. So here the integers will be 1, 2, and 1. So we got these 3 integers. Now place these 3 integers in round bracket 1, 2, 1 in round bracket, and this is called as the mirror indices for this plane PQR. Now let us take the another example to calculate the mirror indices for the plane. Now consider here the cubic lattice structure. So you can draw the cubic structure. Okay. Now label X, Y, Z axis. And here, suppose let the plane ABCD, the plane A, B, C, and D plane. Suppose intercepts along x-axis at the edge length A. Then how to calculate the Miller indices of this plane? First step is write its intercepts along the axes in terms of ABC, that is the lattice constants or lattice parameters. Before writing the intercepts, Understand when this plane is in intersects to the x-axis, then naturally this plane is not intersecting to y and z axis. So we can say this plane is parallel to y and z axis. And when the plane are parallel to the axis, so the intercept of the parallel to the axis is considered to be infinity. So what are the intercepts for these planes? Along x, it is along x is we can write 1a, then it is parallel to y and z axis. So it is you have to consider the intercept is at infinity, multiply by the b, means it is infinity. Write down multiply by the b. So infinity to b is the b infinity, and since it is parallel to z axis, so you have to multiply its corresponding lattice parameters. So take its coefficient or divide by a, b and c. So we will be have the value 1 a by a, then infinity by b into b, then infinity into c by c. So we have the number 1 infinity infinity. Now in this case, in these integers, to avoid this infinity, you have to take the reciprocal. So reciprocal is required to avoid these infinities in integers. So take the 1 by infinity, 1 by infinity. So it is 1, 0, 0. So here is no fractions. Finally you have to reduce to its smallest integer values. Now this is the smallest integers, and we can put this in the parenthesis 1, 0, 0 without any commas. So here is the comma, but in the round bracket, if these integers are right in round bracket, so that represents the Miller indices for this ABCD plane which intersects at x-axis to the x-axis. So this is one example. Similarly, you can take any plane which intersects along y-axis, which intersects to the z-axis, and you can easily write the Miller indices for the plane which intersects to the y, and that Miller indices for the plane which intersects to the y-axis, perpendicular to y-axis. So that will be the Miller indices will be for this in plane. This plane is 0, 1 and 0. Similarly, the plane which intercepts to the z-axis, the Miller indices for this such a plane will be 0, 0, 1. Now here, remember, if the plane to the negative axis intersects to the negative axis, suppose the same ABCD plane which intersects to the positive of the x-axis, and if the plane which intersects to the negative of the x-axis, so what will be its Miller indices? So when this plane to the negative of the negative axis, x-axis, when intersects, its Miller indices will be written as 1 bar 0, 0. So that's where this 1 bar 0, 0 in round bracket that represents the plane which is intersects to the negative negative x-axis. Similarly, you can write for other planes which are to the negative axis of y and z. So these all these planes which are under family of 100, means we can write here, since this is a place here, so write down to this in curly bracket 100 in curly bracket. So all that planes, that is 100 0 10, then 001, and all the planes which are to the negative axis intercept, that is 1 1 bar 0 0 bar 0, and third is 0 0 1 bar. So all these 6 planes are under the family which is written as curly 100 in curly brackets. So this is called as a, this all 6 planes are called as a family of this 100 which are written in curly bracket. Okay, let us erase all this. Now I can take one example. Suppose if we have the intercept at the A along x-axis, B, so this is the lattice parameters A, B, and this is the C along z-axis. And if we draw the plane simply in between these 3 points, this is the B. So you can directly write its Miller indices. As you know, the intercepts is 1A, 1B, and 1C. Then divide by A, B, C to the corresponding numbers. So 1A by A, then 1B by B, then 1C by C. So this is 1 1 1. So these integers directly can write in the parenthesis, and it will be without commas, represents the plane, means Miller indices of this given plane. Okay, now let us discuss about the Miller indices for directions. How to calculate the Miller indices for directions? First, draw the vector and find the coordinates of this vector. Head, suppose be denoted by h1 k1 l1, and the tail denoted by h2 k2 l2. Remember here, this vector should start from origin. Any corner of the cube can be taken as a origin for this vector. So here selected here in this figure, the one origin from along x, along y, along, so it is shown 3 different vectors. Now to calculate the Miller indices for these directions. So what to do? Subtract these coordinates of tail from the coordinates of head. So in this case, the head is the origin, that is 0 0 0, and the tail is the 100. If there are the fractions, remove that fractions by multiplying by smallest possible factor. If we enclose these numbers in these coordinates in square bracket, that represents the Miller indices for directions. Now take one example. Again, take the pen, draw the cube. Okay, suppose this is the cube, sorry. This is the vector. If you consider here, this is origin and this is the end point of this vector is A. So OA vector. What is the direction of how to calculate the direction of this OA vector? So the origin, the coordinates of this origin is the 0, 0, 0. So now the A point is supposed to be considered to be the coordinates of the A point is 1, y coordinate is 0 and z coordinate is 0. So after subtracting this, you will find 1, 0, 0. So here no fractions. Put these integers 1, 0, 0 in the square bracket. It represents the direction. So this is the Miller indices for the direction. So all parallel vectors, if you draw this vector, this vector, this vector, so all these parallel vectors have the same Miller indices. That would be 1, 0, 0 in square bracket. Similarly, draw any vector and find out the Miller indices for these vectors. Okay, now the important features of the Miller indices. Crystallographic points, directions, and planes are specified in terms of indexing schemes. Crystallographic directions and planes are related to the atomic linear densities and the planar densities. And all parallel planes and directions have the same Miller indices. And as we have discussed, when the plane cuts to the negative side of the origin, corresponding index is negative. For cubic only, plane orientations and directions with same indices are perpendicular to one another. So here, remove this. The Miller indices are used to describe planar in a crystal lattice. And these planes may be used to describe a surface of a semiconductor materials. And the material properties along any directions in a family are the same. This is all for today's lecture. Thank you.